All right, today we're taking a grand tour, not to some far-off galaxy, but to a place that's way more mysterious and a whole lot closer to home, the very center of our own planet. So, have you ever really thought about what's thousands of kilometers directly under you right now? We're talking layers of molten metal, superheated rock, and pressure you can't even imagine. But how could we possibly know what's down there? Well, that's the big question we're digging into today. You see, the key to unlocking our planet's deepest secrets is the science of geology. It's the field that studies Earth's structure, its long history, and all the incredible forces that are constantly shaping and reshaping our world, even as we speak. And that means our guides for this trip are geologists. You can think of them as planetary detectives. They use clues they find on the surface to piece together this amazing picture of what's happening in the deep, unseen layers of the Earth. Okay, our journey starts right now. We're going to travel from the surface all the way down to the very core, exploring each layer one by one. And here's our map for the descent. The Earth is made up of these really distinct layers, kind of like a giant onion. So let's start at the very top. Our first stop is the crust. This is the ground beneath our feet, right? The continents, the ocean floors. It's the part of the Earth we know best, but it's also, by far, the thinnest and most delicate layer. I mean, the crust is surprisingly thin. It's basically just Earth's outer skin, anywhere from 5 to 40 kilometers thick. And it's not all the same either. The crust under the oceans is mostly a dense rock called basalt, but the continental crust, the stuff that makes up the land we live on, is made of lighter rock, like granite. And that difference in density, it's going to be super important later. All right, now we're plunging deeper. We're leaving that thin crust behind us and entering the mantle. This thing is a massive layer of superheated rock that makes up most of our planet's volume. Get this, the mantle is a staggering 3,000 kilometers thick. Its top part is rigid, and it combines with the crust to form what we call the lithosphere. But right below that, you hit the Asthenosphere. And here the rock is so hot and under so much pressure that it actually flows, kind of like super thick tar over millions and millions of years. This slow, powerful movement is literally the engine that drives all the changes we see on the surface. We've reached our final destination. We are at the center of the Earth, the core. This is the planet's engine room, a place of extreme, incredible heat and pressure, and it's made almost entirely of metal. Now, the core actually has two parts. First, there's the outer core. It's a churning ocean of liquid iron and nickel. And the motion in this metallic sea is what generates Earth's magnetic field, that vital shield that protects all of us from harmful solar radiation. Then, at the very heart of our planet is the inner core. It's a solid ball of iron and nickel. And it's not solid because it's cold. It's as hot as the surface of the sun. It's solid because the pressure down there is so absolutely crushing that the atoms can't melt. So we have this beautiful, detailed map of what's inside the Earth. But that brings up a pretty big question, doesn't it? I mean, we've never drilled past the crust. No person, no machine has ever visited the mantle or the core. So how on earth do we know what's there? It's a fantastic and perfectly logical question. And the answer, believe it or not, comes from listening. Geologists listen to the echoes of earthquakes. When an earthquake happens, it releases this immense energy in the form of shockwaves. We call them seismic waves, and they travel right through the entire planet. And these waves move incredibly fast. A primary wave, or a P wave, can travel through the upper mantle at an average speed of 8 kilometers per second. Just to put that in perspective, that's fast enough to cross the entire United States in about 8 minutes. So here's the secret. Just like light bends when it goes through water, the speed and the path of these seismic waves change depending on the stuff they're passing through. So by measuring when and where these waves pop up at thousands of stations all over the globe, geologists can basically reverse engineer a map of the Earth's interior, figuring out what's solid, what's liquid, and how dense it is. It's genius. Okay, now that we know the layers and how we see them, let's connect that deep interior to something huge that happens right up here on the surface, the creation of our ocean floors. Remember that flowing part of the mantle, the Asthenosphere? Well, that movement pushes molten rock up through these giant cracks in the ocean floor, which we call mid-ocean ridges. As this stuff erupts, it cools, turns solid, and literally pushes the older rock away on both sides. brand new seafloor is being created constantly. And we have some seriously compelling evidence for this. First, geologists find these weird pillow-shaped rocks at the ridges, and those can only form when lava cools down really fast underwater. Second, there are magnetic stripes in the rock on the ocean floor, which is like a perfect recording of Earth's magnetic field flipping back and forth over millions of years. And finally, when we drill down, the samples confirm it. The farther you get from a ridge, the older the rock is. But wait, if new floor is always being created, why isn't our planet just expanding like a balloon? Well, it's because for every bit that's created, another bit is destroyed. In other places, the dense ocean floor actually sinks back down into the mantle at what are called deep ocean trenches. This recycling process is called subduction, and it perfectly balances out the creation happening at the ridges. So let's just pull all this together and look at the big picture, tying the heat from the core all the way up to the movement of the crust. Think about the timescale here for a second. This whole process is so constant that the entire ocean floor gets completely renewed, totally replaced about every 200 million years. Our planet is in this perpetual state of remaking itself. It's just incredible. And that right there is the biggest takeaway. Our planet is not some static ball of rock. It's a single, dynamic, deeply interconnected system. The intense heat from the core creates movement in the mantle, and that movement in the mantle is what drives the creation and destruction of the crust that we all live on. Which leaves us with a final, pretty fascinating thought. This whole process is happening right now as you're listening. The Atlantic Ocean is getting wider, the Pacific is shrinking. So, knowing that the entire ocean floor gets a facelift every 200 million years, what do you think our world map is going to look like 200 million years from now?